As we wrap up Chapter 11 on energy and its conservation, we are going to look at another way to transfer energy in Chapter 14 through vibrations and waves. We have already discussed vibrations through simple harmonic motion when we talked about the pendulum and a mass on a spring. As you can see, both of these objects are displaced from equilibrium by a given force. And then there is a restoring force that would get the object to accelerate back to its equilibrium point. If we look at the equations for the pendulum and the mass on a spring, we see that they're very similar. The period of a pendulum, or how long it takes to complete one cycle, is equal to 2 pi times the square root of the length of the pendulum over the acceleration due to gravity. And we saw before in our Paul Hewitt video that when we looked at rotational inertia, the length of a pendulum will determine how long it takes the pendulum to swing. Shorter pendulum swings faster. We looked at last chapter at a mass on a spring, where we had the period of the mass on the spring is equal to 2 pi times the square root of the mass over the spring constant. So where the length of a pendulum determines its period, the mass on the spring will determine its period. And the K in that equation, again from last chapter, is Hooke's law. It's the stress, or the force applied to the mass, over the strain, which is how far it is displaced, is equal to a constant. That constant is called the spring constant. So as we said, both of these exhibit displacement from equilibrium and a restoring force to accelerate it back. As we start to look at waves, we can describe them in the same way that we have been describing simple harmonic motion, or pendulums and springs. They are in fact back and forth vibrations. We can also call those oscillations. They also seek to restore the particle to equilibrium, and we can model a wave by the familiar sine curve. When we talk about waves, we have to discuss what travels in waves. We know that light travels in waves, which is electromagnetic energy. Everything on that spectrum, sound, TV, radio signals, water and other fluids, and vibrating strings also show wave properties. So what is the purpose of a wave? Waves are to transport energy, as I said in the introduction. However, they transport energy without the full-scale movement of matter. What that means is that the particles of matter will vibrate right to left, as in the simulation, or up and down, but they do not move measurable distances. In other words, that first spring pushes the second spring, which pushes the third spring, etc. On their own, they don't move very far, but they will transport energy over long distances. Just think about being at the ocean. The water that's way out, a mile out in the ocean, is not the water that you will eventually feel on shore. It just pushes the same water vibrating back and forth, back and forth. So we can use water waves to help us understand and to model some wave behavior. We have two different categories of waves and different ways to describe how waves interact. We have a longitudinal wave. To make a longitudinal wave, you can just picture a slinky attached to a wall that you're moving left to right. A good example of a longitudinal wave that we will study more in depth is a sound wave. So the energy is transported to the right, and the particles are moving parallel to that energy transport, right to left. A transverse wave, such as electromagnetic waves, including light, which we'll study in a later chapter also, and a vibrating string, also transport energy to the right. However, the particles will move perpendicular to the energy transport. So the source is moving up and down. And you see that slinky, if you took the same slinky and attached it to a wall and moved your hand up and down, you could see that the particles are moving up and down, which is perpendicular to the direction of energy transport. Another way that we can classify waves is whether they are electromagnetic or mechanical. The major difference between electromagnetic and mechanical is that an electromagnetic wave is capable of transmitting energy in a vacuum. They don't need anything to move through. They don't need air, they don't need water, they don't need any medium. A mechanical wave that we're going to talk about in this chapter, such as sound, requires a medium to transmit energy. Sound will not travel in a vacuum. It needs air, it needs water, it needs something to travel through. So when we look at waves, we're going to start classifying them into different categories and then start talking about their behavior based on those categories. So that's just a short introduction into waves that will help us later develop a deeper understanding of how they work.